hello, and this is the problem. This is the code I wrote. Let's first read some description. There is a robot on an M by an M into N grid. The robot is initially located at top left corner, and there is a finish point at bottom right corner. We have to make a robot reach this point, and the condition is it can only take one step at a time. Like it can only move to either right or down at a time. So just have to return the all the possible unique paths that exist, like number of unique possible paths that the robot can take to reach the bottom right corner. Okay, we are not actually given an grid. We are simply given these indexes, and well, it's not very difficult problem if you know a bit of recursion, since we can move either to the either to the right or down. So we know, okay, there two calls at each level. Our tree will branch out into two paths. Okay, and forget the robot. We simply start from here. We simply start from this point, and we can go either up or to the left. So if this is M into N matrix, so if you draw this, I tried drawing here. It's very basic. So if it's M by N matrix, then okay, for the left call we are just decreasing M by 1. In the right call we are decreasing N by 1, and it's and that's all you need, really. But if you just submit if you don't use memoization in this approach, which is basically using an array to store your results, so you don't have to calculate everything again and again, right? If you don't use memoization, you will have some problem submitting this solution. I think some time you just hit some upper time limit. Okay, so yeah, this is also easy. You can just simply put this condition: if M, okay, when both my M and N are 0, then return 1, and when either of them becomes less than 0, then that means that it's not a valid path. Return 0. Okay, store my result in this array, fine, and just add all these all the paths we have got and return this. Okay, very easy. Now okay, let me show you something. There's another way to do this. I mean, there is not another way, but there's like a very slight change in this solution. If you look at this, it says when both M and N are equal to 1, return 1. Why is that? In this one, we are checking 0 in M and N we are checking for 0. In this one we are checking for 1. Why is that? This is Gaussian solution. Here, this is what I was. Let's just copy this code. So yeah, as you can see, so the reason for that is, and also I have also changed the second condition. Now we are checking if either of them is smaller than 1. Previously we're checking if either n or m is less than 0. It's because in this solution I am adding an extra row and column to my array, and if I just run this, you can see this is the extra column. This way it's column, right? Yeah, so this is an extra row, this is the extra column, and since it's not really the part, like our matrix is smaller than this, this does not serve any purpose, this extra row and column, and by setting it to 1 we are actually checking the number of possible ways to get to this point, 1 1, and it is the same thing. If the extra row and column were not present, if we somehow got rid of this, we would still be looking for ways to reach here. Okay, so that was the reason for this. What else I found? I'm just I noticed like one couple more things. Well, it will still run. Yes. Why? Because here I'm doing n minus 1, m minus 1. If I don't do this, if I don't decrease my index by 1, I will get out of bound exception here, because it's pretty obvious, right? Because even though I'm using mn here, imagine I'm being imagine if it's a m 0 0. Okay, on. 0. So this is what 3 into 2 array looks like. We have because it's 0th indexed, So that's why this step is important. Okay, enough. That was a good explanation. What is the space and time complexity? For space complexity, we are using this array, so it's taking extra memory, m into n. Space complexity is m into n. The time complexity is it's not exponential, even though here it looks like that for at each call, at each level, the tree is branching out into two ways. It certainly looks like that, and this is what happening. But we are storing the result of the calculation into this array. So we are not calculating the same path again and again. If you try to draw this, if you try to draw the recursion tree, you will notice that there are a lot of similar calls. It's basically creating, yeah, like a lot of similar calls, and if you store the result of some call, you don't have to like I would have I would like to have some uh, example with me right now, but yeah, anyway, uh, let me see. Okay, here, for example, I took this path to y1, this call, and eventually I found the answer. uh, I found the answer for 1. Let's say it's 1. So now in some other part of the tree, when I when I uh, when I have to 1 call again, I don't need to calculate. I don't need to go further down, right? I already have the answer. Without memorization, this is exponential time complexity, but with memorization, it is m into n. Okay, yeah. So this is for this question, and the next question I did was kth smallest element in binary search tree. So if this tree, we have to return the kth smallest value of all the values in the tree. Okay, what, because it's a binary search tree, sorry, because it's a binary search tree, I know that the smallest value in the tree, it's gonna be here, the what, the left left leaf, right, the end leaf. So if this is tree, this is the smallest value, and we have to return the kth smallest value. So kth, third smallest value, it's for first index. So this is the first smallest value, this is the second smallest value, and this is the third smallest value. We have to return the 3. Now let me show you. Yep, this. Here I am doing it iteratively using a stack. This problem is very similar to was what's the name of the problem? Okay, there is a very similar problem, and it's like, of course, obviously binary. Okay, it's very similar problem to this. I don't remember the name right now. But yeah, we are using stack. Let me just show you an example. Yeah, so pushing the nodes onto the stack, and then when I get here, no, actually, I'll not get here. I push one onto my stack, and then there is a null. This condition hits. I get out of this while loop. Now I start popping elements off the stack. This is the first element to get popped off, and then I'm checking if my I is one in first indexed, so it's starting from 1. Here it's null, right? So this is yes. Once my I becomes equal to k, I return whatever node it is. I return its value. Here I have null. I come here, since we just need the first indexed node. This is it. This is the smallest one. But okay, so this is done using a stack and iteratively, and then I tried using recursion. Then I tried using depth first search. Here. Just okay. So here's the depth first search, and well, because it's recursion, I have to okay. Let me. Yeah. We have to keep global states and ignore this result for now. Imagine it's not here, right? When I was writing this, there was only this I, which I was using to keep track of the index, and imagine it's set to 1. Okay, so I run depth first search on this tree. Let's see what happens. We are at 3, and then we check the right side. We are at 1, and then we are at null. At null, we return 0. So this call returned 0, but since it's not set to any variable, the 0 gets discarded, right? And then once I get out of this call, well, when would I get out of this call? When I found a leaf node. This is a or when I have found a smallest node, right, on the left side, in the left subtree, I mean. So this is D1, and when I got out of this call, I check, okay, is my I equal to k? If it is, then return the root. I plus plus, increment my I, and then check the right subtree. This code will not work because I very naively, well, yeah, I very naively put this thing here. Return null. When I becomes k, return null. Try to find a problem with this. Okay, I tell you. Uh, I think I spent good 20 minutes just trying to figure out why this was not working. The reason this was not working is because of returning. It occurred to me, oh, we are inside of a recursion tree. This root or root's value, whatever this return is returning, it's not returning it to me. It is returning it to its parent caller, because we are inside of a recursion tree. We are not at the top, right? And yeah, sometimes you kind of forget these kind of details. But yeah, that was interesting to know. Okay, so what's the improvement? Here is the improved solution, the one that works. Instead of returning, I stored the result in my result, and here I defined the result, and I fixed my I. It was set to 0 in the previous code slab. Okay, and now it works. It still visits the entire tree, and only at the end does it return the answer. I think there's a way to change this. I think there should be a way to uh, like propagate some kind of signal up the recursion stack that okay, we have found an answer, let's return, let's break, let's return early. Yeah. What else? Let's see. Sure. What is the time and space complexity here? It's linear. Space complexity is linear because we are making use of recursion call stack. So that is linear. The first search is linear, or H if you want to say you prefer that. Because we are visiting we are visiting every node in the tree. So yeah, it's linear solution. Linear space complexity, linear time complexity. Can I verify it? Yes. Okay. What is the time complexity here? With iteration. I think it's same. Yeah. Because we are making use of a stack. So that's linear. And this is also linear. Wait. What is the time complexity of this? Should be linear. Iterative in order traversal. Yes, this is the key point. This one stops early, so it's a bit more efficient than a depth first search. Okay, okay. Yep. Okay, so these were the problems for today. Thank you so much for watching.